You may not have noticed this, but most of the tests that we've considered so far have a hypothesis requiring that the terms be positive. So what happens if you have a series that contains negative terms? In section 9.6, we will examine alternating series, specifically the alternating series test. Now, let's be clear on what an alternating series is. In an alternating series, the signs of consecutive terms strictly alternate. That means the sign switches with every other term. In example 1, we will determine if these series fit that definition. Example A, we have the sum from k equals 1 to infinity of negative 1/2 to the k power. An easy way to determine if this is an alternating series is just to generate the first several terms of the series. So if k is equal to 1, we have negative 1/2 to the first power. For k equals 2, we have negative 1/2 squared. K equals 3, negative 1/2 cubed. And then k equals 4, negative 1/2 to the fourth. So that's enough of the terms to make our conclusion here. When we have a negative number raised to an odd power, the result is negative. So the first term is negative. The second term, we have a negative number raised to an even power that gives us a positive result. The third term is a negative number raised to an odd power, so it's negative. Now, you can see that every other term is going to alternate between an even power and an odd power, so every other term switches sign. Therefore, this one is an alternating series. That's important to recognize because it will qualify for what we call the alternating series test in determining convergence. Now, the presence of this negative 1 raised to the k power is what caused that series to alternate. Another way that this might appear is in the form of a trig function. Think about expanding this one, the first several terms. If k is equal to 1, we have cosine of 1 pi divided by 1 squared, or just cosine of pi. For k equals 2, we have cosine of 2 pi divided by 2 squared, or 4. For k equals 3, we have cosine 3 pi over 3 squared, or 9. Let's do one more term. For k equal to 4, we have cosine of 4 pi divided by 16. And then this goes on and on and on. Now remember, for odd multiples of pi, cosine of pi is negative 1. But for even multiples of pi, cosine of that even multiple is positive 1. So because the argument alternates between a positive multiple of pi and a negative multiple of pi, this is in fact an alternating series. So one way to recognize the alternating series is to spot the presence of a negative number raised to a power. Another way to do it is to recognize cosine of a multiple of pi. Let's see if that pans out on our next series. Again, we're just going to examine it by expanding it for the first several terms of the series. So if n is equal to 1, we have sine of 1 over 1. N equals 2, we get sine of 2 over 2. N equals 3, we get sine of 3 over 3. And for n equals 4, we have sine of 4 over 4. And this continues. So this time, instead of having multiples of pi in the argument, we simply have integer values. So the arguments of these sine functions are radians. Let's visualize the unit circle to determine the sign of each of those terms, or just type them into your calculator in radian mode. So thinking about the quadrantal stops on our unit circle, we start at 0 radians, then we come up here to pi over 2 radians. That's about 1.57 or 1.6 radians. At pi radians, we know that's about 3.14. At 3 pi over 2, it's approximately 4.7 radians. And then when we get back to 2 pi, that's about 6.3, rounding to the nearest tenth here. So when I want to evaluate sine of 1 radian is somewhere over here in quadrant 1. The sine of sine in quadrant 1 is positive. Sine of 2 radians then would be somewhere over here in quadrant 2. Sine of an angle in quadrant 2 is positive. Sine of 3, we're still over here in quadrant 2, so this is a positive term. And then finally, sine of 4 lands somewhere over here in quadrant 3. The sine of sine in quadrant 3 is negative. So this series will have some positive terms and some negative terms. But technically, it is not an alternating series, because every other term does not change sign. So this one would not qualify for what we're going to learn about called the alternating series test. So if we can verify that the series that we're dealing with is alternating, here's how we determine convergence. The alternating series, -1 to the k plus 1 times a sub k, converges provided both of the following are true. Now, as we read these conditions, notice that it's going to refer to a sub k, where a sub k is really the substance of the series. So I'm separating the substance of the series from the term that causes the sign alternation. That can be a negative raised to an exponent, that could be cosine of a multiple of pi, or that might be sine of a multiple of pi over 2. So I'm just going to examine a sub k. The terms of the series are non-increasing in magnitude. Now, this is similar to, but not exactly the same as decreasing, right? Non-increasing means it is either decreasing or staying the same. And again, it's talking about in magnitude, so we're just looking at the substance of this term. What this looks like technically is that a sub k is greater than or equal to a sub k plus 1. So the term that comes first is going to be either bigger than or the same as the term that comes next. Both of these are positive terms, so we have greater than 0 here, because remember, I'm just examining the substance, I'm ignoring the sign alternation factor. Now, this doesn't have to be true for the entire series. It doesn't have to be non-increasing at the very beginning of the series. This only has to be true for some, we're going to read this backwards, for some subscript k greater than or equal to capital N in the natural numbers. What in the world? Can you read all of that notation? Let me draw you a picture to help you understand what all that's about. So let's assume that we're going to plot our series in the plane. So along the horizontal axis, we're going to keep up with subscript, and on the vertical axis, the value of the term of the series. So we're looking at natural numbers here, 1, 2, 3, ... So actually, I need to call this k since we're using the index k. So remember, when we plot a series, the graph is discrete points, right? So they're spaced out something like this. Now, what we're going to see in a non-increasing series is that it's non-increasing beyond some specific point. So observe the way that I've drawn this particular pattern. It's increasing at first, but once I get beyond this subscript, then the rest of the time, that is until infinity, it is decreasing or non-increasing. So there is some index that happens to be a natural number, because remember, we use the natural numbers to count the position of each term in the series. So beyond some specific point, right, for every subscript greater than or equal to n, for every subscript beyond this particular point, then the series is going to settle down and be non-increasing. So if we can establish that particular inequality, and number 2, the limit as k goes to infinity of a sub k equals 0, then our conclusion is that the alternating series will converge. Now I want to backtrack just a minute to clarify the graph over here. This is a sequence of all positive terms because I'm only considering the substance. I'm not considering the alternation part. If I were to actually graph the series, or the terms of the series as they're written here, we'd have some above and some below. So it's going to hop up and down and do something like this. Okay? So let's see what this feels like in practice. Example 2, apply the AST alternating series test to determine if the following series converge or diverge. So we have the sum from k equals 1 to infinity of negative 1 to the k over k times natural log squared of k. The presence of this term right here causes it to be an alternating series. So ignoring that part and looking at just the substance of our formula here, a sub k is this 1 over k times natural log squared of k. We want to show that it is non-increasing. That is, I want to establish this inequality here. So I want to show that a sub k is greater than or equal to a sub k plus 1. A sub k is given in this formula, 1 over k natural log squared of k, and a sub k plus 1 then is 1 over k plus 1 natural log squared of k plus 1. At this point, we don't know if this is a true inequality we're attempting to find out. So my natural instinct is to go ahead and cross multiply to get rid of the fractions. But remember, we have to know the sign of the factors we're multiplying by so that we know which direction that inequality should face. If you multiply both sides by a negative, you have to reverse the inequality. So all of these terms are going to be positive. The natural log there is squared. When we square something, it's always positive. And k and k plus 1 are both positive for k equal to 1 or larger. That simply means it is legal for me to cross multiply without having to change the direction of my inequality sign. Now we can observe this inequality, and it should be obvious that it is true for all k. Now, it should be obvious, but maybe it's not obvious. How can I tell? Well, I'm going to compare factor by factor. If I compare this factor to this factor, clearly the factor on the left is bigger. Also, if I compare my natural log squared of k plus 1, because it has a larger argument than this one, and natural log is an increasing function, then the factor on the left is bigger. So you have the product of two factors that are factor by factor larger than these two factors. Therefore, the product on the left is definitely larger than the product on the right. So the first result of the theorem has been established. However, both of those parts must be true. So the next thing we need to do is find the limit at infinity, only of the a sub k part. Remember, we're ignoring the alternating factor. So we're going to find the limit as k goes to infinity of 1 over k natural log squared of k. Very simply, because your denominator is increasing without bounds, the value of the fraction is 0. So since both of the conditions of the alternating series test have been satisfied, we can conclude that the series converges by the alternating series test. Now, the trickiest part of the alternating series test is often being able to establish this inequality. So that's going to be the case on example B. So we have the series from n equals 1 to infinity of sine of 2n minus 1 pi over 2 times n to the 1 over n. Now, first of all, let's observe how this is an alternating series. If n is an integer, then 2 times that integer is definitely an even number. And if I take an even number minus 1, it's definitely going to be an odd number. So I have an odd multiple of pi over 2, right? On our unit circle, all of the odd multiples of pi over 2 will be coterminal with pi over 2 or 3 pi over 2. So the odd multiples of pi over 2 will either be positive 1 or negative 1. So the alternating sign is encoded in this factor right here. That's the same thing as raising negative 1 to a power. So the a sub k, or in this case a sub n part that I need to examine for the alternating series test is this n to the 1 over n factor. Now, I'm not going to take the time to go through it, but if you try to establish the inequality that proves that this is non-increasing, it's really challenging. So another way that you can prove that this is non-increasing is to show that its derivative is negative. If we can establish the fact that this is a decreasing function, then we know that it is non-increasing and satisfies the first tenet of the alternating series test. So let's find the derivative with respect to n of n to the 1 over n. Now, because we have a variable base and a variable exponent, we are going to need a left side over here so that we can apply logarithmic differentiation. Now, I did get a little ahead of myself here, so before we apply the derivative, we've got our equation here, and we want to take the log of both sides. Natural log of both sides, that is. So back on track here, we can find the derivative with respect to n of the left side. Let's go ahead and move that exponent down as a coefficient. And we're going to differentiate this side also with respect to n. Now, I know at this point we've been practicing finding limits so much that you're going to think about, is the left side an indeterminate form? But it doesn't matter because we don't have the limit operator. Our operator is derivative, so I need to differentiate the left side. And that's going to require the product rule. So we'll have the first function 1 over n times the derivative of the second, which is 1 over n, plus the derivative of the first, which comes out to be negative 1 over n squared, times natural log of n. The derivative of the right side with respect to n is 1 over y times the derivative of y with respect to n. As we have seen before with logarithmic differentiation, we need to isolate this term dy over dn, so we're going to multiply both sides by y. So I'm going to do a couple of things here. I'm going to reverse my terms. Here is, again, I'm just reversing the sides of my equation, and I'm multiplying by y. What we have left over here is 1 over n squared minus 1 over n squared natural log of n. Recall then that we can go back and replace y with its original expression. Y represented n to the 1 over n. Let's go ahead and factor out 1 over n squared, so we have left 1 minus natural log of n. Now, n starts counting at 1 and goes to infinity, so n is always positive. If n is positive, then this term is always positive. This term is clearly always positive, so let's talk about 1 minus natural log of n. This term will be positive or greater than 0 if I solve this little inequality by subtracting 1, reverse your inequality sign, n is less than e. So this factor right here will be positive when n is less than e. Think about it. When n is equal to e, natural log of e is 1. If my argument is less than e, then this happens to be a negative number. 1 minus a negative number would be a positive number. So now we can say if it's greater than 0, that factor is greater than 0 for n less than e, then we can say this factor is going to be negative when n is greater than e. So beyond a specific subscript value, beyond a specific position in the sequence, the derivative is going to be negative. If your derivative is negative, the function is decreasing. So we could say the term n to the 1 over n is decreasing for all n greater than or equal to, now e is not a natural number, so I'm not ever going to have a subscript of e, so I'm going to go to the next highest integer and say this term is decreasing for all n greater than or equal to 3. So that establishes the first condition of our alternating series test. The second thing we need to show is that the limit as n approaches infinity of n to the 1 over n is 0. Well, it looks like we're going to need to make use of logarithms once again. So I'm going to take the natural log of both sides. I'm going to reverse the limit operator and the natural log function. And I'm going to take the 1 over n down in front of the log as a coefficient. That was a lot of steps, but I know you've done that a lot of times. Now, if I view this as natural log of n over n, we have the form infinity over infinity. So I'm going to apply L'Hopital's rule and differentiate the natural log of n to get 1 over n, and differentiate the n in the denominator to get 1. And this limit then is 0. So y is equal to e to the 0th power, which turns out to be 1. Now, recall from the alternating series test that the second condition that we're looking for is that the limit is 0. And in this case, we came up with a limit of 1. So the second condition of the alternating series test is not satisfied. We can say, therefore, the series diverges by the alternating series test. Remember, both conditions have to be met. We did find that it was non-increasing, but the limit did not pan out. So this one diverges. All right, let's finish out this video with example 3. Examine the variations of the harmonic sequence and series below. Determine convergence or divergence. So if you compare example A to example B here, example A is the harmonic sequence. Look at the notation. The notation indicates that we're dealing with a sequence, where example B is the harmonic series. So the way I determine convergence or divergence is very, very different. If you'll recall, the way we determine if a sequence converges is simply by finding its limit. If its limit is finite, then the sequence converges, and it converges to 0. So we could say the harmonic sequence converges, and it converges to 0. That means way down the line in the pattern of that sequence, the terms are getting closer and closer to 0. But as we have learned, the sum of the terms of the harmonic sequence, which would be the harmonic series, actually diverges. The harmonic series diverges. You could show this by the integral test, or you could demonstrate that it is a P series that diverges. Both of those would be possible tests to prove that, and we've done both of those in the past. So it's kind of interesting. The harmonic sequence converges, but the sum of that sequence, generating the harmonic series, diverges. So let's see what happens when I introduce this term. So notice here my a sub k term is the same as what we had over here for the harmonic series. So with the presence of this -1 to the k, I'm looking at the alternating harmonic series. Since this is an alternating series, we need to apply the alternating series test. The first thing that I need to examine, is it decreasing or more particular, non-increasing? So if I test out this inequality, knowing that all of those terms are positive, I could very easily establish that this is true for all k. If you want to subtract k from both sides to say without a shadow of a doubt we have a true inequality. So this is going to be true for all k greater than or equal to 1, since that's where we started counting. So far, so good. Now, the second thing that we need to verify for the alternating series test is that the limit as k goes to infinity of a sub k, which in this case is 1 over k, is 0. And that is in fact true for this particular limit. So we can say, therefore, the alternating harmonic series converges by the alternating series test. So where your ordinary harmonic series diverges, if we allow it to alternate, it's going to converge. If you want a visual of this, we can imagine the harmonic sequence and the alternating harmonic sequence. So if we put along the horizontal axis n and along the vertical axis a sub n, then the harmonic sequence does something like this. The sequence converges, but as soon as I add up those values, the series diverges. Now, if we were able to allow this harmonic sequence to alternate, the graph would do something like this. So when I add the terms of that alternating harmonic sequence together, because of the alternation, the positives and negatives, there's enough cancellation that occurs that allows that alternating harmonic sequence to converge. This is going to lead us into something that we call conditional convergence, and we'll study that in the next video. For now, we could say the harmonic series converges provided that it alternates in sign.